pennies or other coins, twisty tie, like one of these from a garbage bag, a towel in case you spill water. Of course, you definitely need a pair of scissors, and a marker, Sharpie or a marker could come in handy. None of these things are going to be showstoppers if you don't have them. And then another thing that might come in handy is like what, a McDonald's ketchup packet, or I have an Arby's barbecue sauce package here, and we'll show you how you can do something with that. But you should be able to get by with just what's in your bag. And of course, the other thing that we told you that you definitely need is a plastic water bottle, and it should be filled all the way to the top with water. This is completely full of water, and then screw on the lid real tight. Maybe not real tight yet. Okay, so we're going to go ahead and get started. So there isn't very much actually in your bag for this one. We do a lot of these virtual programs where we put a little lunch bag like this together with the things that you need, the materials you need for those experiments. And the two experiments we're doing today don't really have too much in them, but you can go ahead and take everything out of there. You should have this thing right here. It looks like an eyedropper. This is called a pipette. This is what scientists use to measure tiny amounts of liquid. Like if they need to add a chemical in an experiment, they might use this if it's only a little bit that they need, because you can actually add a drop at a time, or you might see that the pipette that we gave you has some numbers on it. It's kind of like a ruler. Those numbers are for measuring how much liquid is in there. So that's a pipette, that's in your bag. You should also have two transparent balloons. You'll see when you blow these up that you can actually see through them, which is really handy. But if these balloons pop, or you want to do it more later, any balloon will work. But these ones that you can see through are really nice. And then you should have a little plastic bag that has a couple of tiny little washers. They look like rings. They look like a donut or a ring. That's called a washer. It's made out of steel. You should have two of those, I think. You should have two tiny little rubber bands. And then there should also be two, and don't anybody call this a bolt. This is called a hex nut. It's called a hex nut because hex is, I believe, the Greek or Latin word for 6. And this nut, which goes on a screw or a bolt, has 6 corners. So it's called a hex nut. You should have 2 of those. So that's what's in your kit. The first experiment that we're going to do is we call it a screaming balloon. And if I don't know if you all should have gotten an email that had links to our website. Both of these experiments, both of these activities we're doing today are on our website. Maybe real quickly, I will show you where you can find them on our website, because there are lots of other cool experiments you can see there. So I'm going to go ahead and share my screen. This is our website, coolscience.org. And when you go to that page on a computer, you'll see a nice little video of one of our shows that we do. Maybe soon we'll be able to come to the library and do a show like this. But up here at the top where it says cool stuff, you have a little option called Try Science at Home. And if you click on that page, it's a whole page full of experiments that you can do at home. So the 2 experiments we're doing today, this one called Cartesian Divers, and this one called Screaming Balloons. But there are lots of others that you can do on your own. And if you want to do, and we add more all the time, so you can check that page a lot. If you scroll all the way down to the bottom of that page, you'll see this is actually a little window that shows what our Facebook page looks like. And every day on our Facebook page, we actually post an experiment that we find someplace else on the internet. So these are all from other cool science websites, and they're experiments you could do. Like this one is a gardening experiment, and this one is an experiment you could do with packing peanuts. Every single day, we post a new experiment on Facebook, and you can either go to our Facebook page or just look at it in this window right here. And this is not only a good way to find some cool experiments you can do, but this is also a good way to introduce you to lots of other really great science websites. And if you go to those science websites, you'll see they also have more science experiments too. So we just kind of spotlight one every day. And then down at the very bottom of every page on our website are the buttons for our YouTube channel and our Facebook and our Twitter and our Instagram. I'll just show you real quickly our YouTube. If you click on that, it takes you to our YouTube channel. And we have, I think we're up to about 40 videos on our YouTube channel right now. And so all kinds of cool stuff. And we, it's been a little while since we put a new video up there, but we're putting new videos up there all the time. So you can watch some really cool, these aren't the flashiest videos. They're not the best videos on the internet, but there is some really cool science in here that that will amaze you, things that you've never seen or known before. So you can check that out when you get. So that's all the stuff that's on our website. So these two experiments we're doing today are on the website. And so you can go and check those out later. The nice thing about those pages is that not only do they have all the instructions, I'm going to go through the instructions now, but they have all the instructions there. So you could, if you need to repeat it later and you forget something, but it also has, it really explains the science. So you can read all about the science that's going on. I'll say a little bit today, but we don't have time to really get into all of the science today. So you can read more on the website. And then there are also, each of those pages has lots of links to other cool experiments that might be similar to this one. So if you like one of these experiments and you want to do another experiment like it, or if you want to learn more about some of the science that's in there, the links that are on that page will take you to places where you can read more and do more experiments. So the first experiment we're going to do is called Screaming Balloons. And if you have a penny, we're actually going to do this with a penny first. We're cheap, so I didn't put a penny in your kit. But if you have a penny or any other coin, what you're going to do is you're going to take one of your balloons and you're going to put the penny inside the balloon. I don't know if you ever thought of putting something inside a balloon before, but this is your chance. And you might have to kind of stretch it a bit to get it in the hole and through the neck of the balloon, kind of push it in there, stretch around there, and get it to go all the way into the bottom of the balloon so it'll bounce around in there. Just like that. So I've got a penny in my balloon now. And then now what you're going to do is you're going to blow it up, and you don't want to blow it up too big, especially if you have small hands, maybe just about big enough that you can really hold on to it like this with your hand. And if you don't have a twisty tie, if you have, or I should say, if you have a twisty tie, what I usually like to do is twist the end of the balloon a few times, and then take a twisty tie and tie it shut. If you don't have a twisty tie, you can just go ahead and tie a knot to tie the balloon shut, or have somebody tie it shut for you. And then the air won't come out. The nice thing about the twisty tie is if you want to do a different experiment, all you have to do is take the twisty tie off, let the air out, pull the penny out, you can put something else in there. But I put a penny in mine now. Let me cruise around here and see if everybody's got the penny in their balloon and got their balloon blown up now. And if you're really good at holding on to it, you don't even need to tie the balloon shut. You can just kind of twist it and maybe wrap it around your finger a little bit so the air doesn't come out. And that's another way you could do this experiment, if you can hold on to that balloon without letting the air out. So I've got a penny in my balloon now. And now what we're going to do is just hold it kind of like a bowling ball. So I don't want you to hold it this way. I don't want you to hold it so it swings around like this. I want you to put your whole hand around it like this. That's why we didn't want to blow it up too big. And then I want you to just start kind of bouncing that penny around until something amazing happens. Raise your hand when something amazing is happening in there. It's not bouncing anymore. My penny is spinning around in there really fast. Is anybody else's penny spinning around in there? Just kind of keep gently shaking the balloon. And then after a few bounces, the penny should land on its edge and just start spinning around.
Mm-hmm. I actually did that once.
So you've done this experiment before?
Yeah, I didn't even know it was an experiment. I just shoved coins inside balloons, blew them up really big, and then...
And you got them to spin around like this and race around?
Yep.
And one of the cool things, if you look closely, at this balloon,
so it made a really fun noise.
Yeah, it makes it, well, we'll get to that in a minute. But with the penny, my penny doesn't make a lot of noise. It kind of makes a whoosh sound. but it really spins around there. And when I stop shaking, it keeps going for a long time. It really rolls nicely. The other thing that's kind of cool, these balloons, they put a little bit of powder in them. That helps you blow them up because it stops the balloon from kind of sticking to itself. And so if you look, you might actually see little tracks in the balloon from the penny rolling around in there, in that powder, that dusty stuff. It kind of makes little tracks, which I think is kind of cool too. So that's amazing. So what's happening here is you're demonstrating how easily round things will spin. That's of course why wheels are round, because they roll really easily. And you might think that, gosh, if you just have a penny in there and it just bounces around, it's probably just going to keep bouncing. But it's amazing how quickly it lands on its edge and starts rolling, because that shape is just really good at rolling. It really likes to keep rolling. I'll scare you with a big word that you won't learn until high school, but in science, we say that this penny has a high moment of inertia. You don't have to memorize that. It's just a fancy science way of saying round things roll really easily or spin really easily. And that's what the penny is doing. It's spinning around, and as it spins around, it rolls inside the balloon. Now, what's really cool, if you haven't tied your balloon shut with a knot, you might want to untie it. Let the air out. Yeah, make that funny noise. If you have another penny, or you can do this later, I wonder what will happen if I put 2 pennies inside this balloon at the same time. Anybody got any ideas? What do you think is going to happen if there are 2 pennies in there? Do you think they'll just crash into each other? That's what I always thought. So I'm going to blow it up again. I'm going to kind of twist the end, tie it with my twisty tie again. Now you can see why these twisty ties come in really handy. One thing to be careful about with these twisty ties, sometimes they're a little sharp on the end, so you want to make sure you kind of bend them away from the balloon so they don't poke the balloon and pop it. But there, I tied it shut again. Now I have 2 pennies inside my balloon. And I'm going to do the same thing. I'm just going to kind of shake it. And at first I hear them clanking around and crashing into each other. But it doesn't take very long at all before both of those pennies are rolling around together side by side. There you can see the tracks in the powder in my balloon on my camera. Those 2 pennies are lined up perfectly side by side and spinning around there together. That's really amazing. And I'll be honest, I can't even completely explain the science of why those pennies just don't keep crashing into each other, but line up. I have to think some more about that, but it's really easy. And you might even want to try 3 pennies or 4 pennies or a penny and a nickel or 2 pennies and a dime. You can, I know you guys, when we do this a lot of times in libraries and schools, you guys want to put everything you can think of in there, 20 pennies. So you can try that on your own, but it's really amazing how easy it is to get more than 1 penny to just roll around together without crashing. Pretty amazing. Now, we called this experiment Screaming Balloons, and I haven't heard any screaming yet. Maybe some of you guys screamed when you first saw this because it was so cool, but that's not the screaming we were talking about. If we want this to scream, we're going to use something different instead of the penny. So I'm going to leave those pennies in there. I'm going to use my other balloon. And this time I'm going to take one of those little hex nuts. Okay, one of those little 6-sided nuts that goes on the end of a bolt. And I'm going to drop that in there, just like that. You can see it. There it is. And I'm going to do the same thing again. I'm going to blow up the balloon. Again, not too big. Kind of twist the end and use my twisty tie again. And tie that shut. So now, if you look at that hex nut, that's not even round. Remember I said that the penny rolled so nicely because it's round and smooth. This hex nut's definitely not round or smooth. It's got 6 sharp corners. I wonder if it will roll like a wheel. So I'm just going to start shaking it around, and oh my gosh, almost immediately it starts rolling around in there. And now as it rolls around, I don't hear that whoosh sound that the penny made. I hear a screaming sound. Do you guys hear how loud that is? And the faster I make it roll, the louder it screams. Remember, hold it like a bowling ball. Don't hold it this way and shake it. It's a lot harder to do it this way. You want to kind of hold it with your fingertips, kind of like you hold a bowling ball, and then bounce it around till it starts rolling in there, and it will start screaming. So even though it's not round, it will still roll very easily. And the reason it's screaming is because the penny was round and smooth, so it could roll very quietly. But if you think about it, suppose instead of a round wheel on your bicycle, suppose you put a big wheel on your bicycle that was shaped just like this hex nut, had 6 sharp corners, and now you went out and rode your bike. Do you think that'd be a pretty bumpy ride? That would be a very bumpy ride on your bicycle. There are actually some videos on the internet of bicycles that have strange shaped tires. And if you have the right kind of road, you can actually ride a wheel, a bike wheel with the strange, but I'll let you find those on your own. But this one, this hex nut, it has those corners. And what that means is as it rolls around like a wheel, instead of rolling smoothly, it kind of bounces from corner to corner, just like it would if you put a wheel like that on your bike. And that bouncing is making the balloon vibrate. When something vibrates, it's moving back and forth really fast. Well, could be really fast. In this case, it's really fast. And that vibration is what makes that sound you're hearing. So it's making that sound because of the corners on the hex nut bouncing and making the balloon vibrate. Now, the reason I told you a marker would be really handy, what we like to do, we do this activity all the time, and we like to draw scary faces on it. So I'm going to draw a scary face on mine. Little marker. Ooh, give him some teeth. So there, I got a scary, spooky face on it. And if I shake it around till I get it going there, I think it looks like a screaming ghost head. So we like to do this at Halloween and call it a screaming ghost head. So I'll let you guys do that later. So that's our screaming balloon. And of course, I know what you guys are thinking. I wonder if I put a penny and a hex nut in there, or if I put 2 hex nuts in there. So we'll let you try that later. But that is our screaming balloon experiment. That's the first one. And like I say, if you go to our website, and while you're finishing up, I'll show you that page again and show you where these links I was telling you about. So if we share this again, so this is that Try Science at Home page. Here's screaming balloons. And you'll see how the page tells you all the materials you need, tells you the step-by-step procedure. Here's where it explains the science, so you can read more about the science. I explained most of it, but there's a little more in there if you want to read. These are some other activities you can do, like putting more pennies in there or trying some different things. This is where it talks about putting a spooky face on it. And then here are those links I was telling you about. So you can see how we have lots of more links to try some similar experiments and there's some videos, just some other cool things you can do here that are related. So that's all on the Screaming Balloon page. Okay, was that pretty cool? Thumbs up, everybody, if that was fun. All right, that was our first experiment. So that experiment, the science we used there was called physics. Physics is a science all about energy and motion and forces. And that motion we were talking about is something called rotational motion, spinning. So that's what the screaming balloon was all about. Now we're going to do some more physics. For this experiment, we're going to make something that we call a Cartesian diver. Might have to reset my camera here. And on our website, it's that page called Cartesian Diver. Really, the way we're going to do it, because there's a lot of different ways we can do this experiment, and I'll talk about a couple of the others later. But the one that we're going to do is really more like a submarine. Maybe we should call this a Cartesian submarine experiment. And we're going to do it with this pipette. And actually, we're not even going to use the whole pipette. We're just going to use the fat end. This is called the bulb. By the way, if any of you will give you a quick instructions on how you use a pipette. So to use a pipette, you grab it by the fat end like this, and you put the skitty end in a liquid like water, and you squeeze the top. This is called the bulb. You squeeze the bulb really hard, leave it in the water, and then let go of the bulb, and it should draw water up just like a straw, and that the stem, the long straight part of the pipette, should have water in it. And now's where you can use those numbers I was telling you about to measure how much is in there. Those numbers are measuring what we call milliliters. Milliliter is a small amount of water. And this pipette will hold 3 millimeters. You can see where it says 1, 2, and 3. And then by maybe filling it up with water, and if you start off at the 3 and you slowly drip it out until you get down to the 2, that tells you 3 minus 2, you dispensed, you squirted out 1 milliliter. And that's how a scientist would measure how much liquid they have. So go ahead and squirt all the water out. We want it to just be empty. And what we're going to do with it, now we're going to destroy it. I know you guys probably like to destroy things. We only need the fat bulb end. So if you look on the stem, you'll see where it says 1 milliliter, 1 ml, 2 ml, 3 ml. I want you to cut it right here between the 2 and the 3. Let me switch to my other camera so you can get a close-up look before you cut. I'll show you exactly where to cut it. It's not really important that you cut it in that exact spot, but here's mine. I can even zoom in here. Bear with me while I refocus. There we go. And so now you can see where it says 1, 2, and the 3's way up here close to the bulb. And there's a line halfway between the 2 and the 3. That's 2.5. And that's where I want to cut it. I want to cut it right on that line between the 2 and the 3. I'm just going to cut all the way through like that. And so it'll look like this now. And then this other end, you can save that because you might think of something cool to do with this other end. It's kind of like a straw, but it's a straw with a really small diameter at the end. And you might think of something cool to do with that. So I wouldn't throw it away. I always like to save everything. And I might, you never know when you might come up with something you can use that for. We might even show you one thing you can do with it in a minute. But now you're going to have the bulb and a little bit, about a little over an inch of the stem left on there. That's going to be our submarine, believe it or not. And we're going to do an experiment now that demonstrates exactly how a submarine works. Maybe somebody can tell me, who can tell me what a submarine is? What's so special about a submarine? I think you guys probably know it's some kind of a boat. What's something special about a submarine? How about, I see it says Erica. I don't think that's an Erica, but it says Erica. Is that an Erica? Oh yeah, okay. You're so far away, it's hard to tell.
I'm actually Eleanor.
Oh, you're Eleanor, okay.
The Zoom name is Erica. Anyway, a submarine, it's like a boat. It's like a boat that goes underwater.
Underwater, so a submarine could go underwater, and you forgot the most important thing. It can also come back to the surface. That's really important. It's a lot of boats can go underwater, sometimes not when they want to, but a submarine could go underwater and it could come back to the surface. Like I say, if you're in the submarine, that's very important. All right, perfect. So we're going to turn this into a submarine, and it's going to work just like a real submarine does. All right, so let's do that. Let me switch back. Well, actually, I'll just do it right here. All right, so you've got your little pipette that's cut off there. Now I want you to grab one of your washers, just like this, and 1 or 2, I think I gave you 2. You only need 1, but you can use both of those little rubber bands. Maybe I need to move everything over a little bit. There we go. All right, and what you're going to do is you're going to put the washer on the end, on the stem of the pipette, just like that. And then take your rubber band and wrap it around the end 2 or 3 times. And that's just to keep the washer from falling off. Okay, so it should look like this. If you want to, you could even put your other rubber band on there too. And if you've never done this before, some of you guys who put rubber bands or scrunchies in your hair, you probably know exactly how to do this. You just kind of put it around there, kind of pull it out, twist it to make an X, and then wrap the other end around there, and do that 2 or 3 times until the rubber band's on there, just tight enough that it keeps the washer from falling off. Okay, everybody hold it up when you're ready to go on that. All right, and I'm going to switch back to my other camera. There we go. All right, so it should look just like this. So we've got this little thing, it's got a hole in one end, it's open in the end. And now what we're going to do, if you have a glass of water, you can do it in a glass of water. If not, you can put it in your bottle, but it's easier to do it in a glass of water for right now. I want you to take it with the hole, the open end down like this, so the bulb up at the top. I want you to drop it in your glass of water. What's happened? What does it do when you drop it in the water? Does it float or sink? Who says, whose is floating? Floating. Okay. Is anybody sinking? I hope not. Oh, I see a hand. That doesn't mean it's float, or it doesn't mean it's sinking, does it? Everybody should be floating. Okay. Why do you think it's floating? It's pretty heavy, isn't it? I mean, it's got that metal washer on there. It's made out of plastic. I don't know. I think it might be heavy enough it should sink. Can anybody tell me why it's floating? It should be floating, really. A lot of the bulbs even sticking out of the water. Let's see. Let's ask. It just says SM. Who's SM?
Because the air in the top.
Oh, there's air. Where's there air?
In the top.
Inside the pipette,
inside.
it's full of air, right? Remember, I said it was empty, or probably I think I said it was empty, but it's not really empty. It's got air in it, okay? And that air in it makes it float, okay? Actually, this demonstrates something called Archimedes Principle. I think there's a link to that on the Cartesian Diver page that you can look at later that explains what's happening. And because this pipette is so big, it has to push water out of the way. And if what's inside the pipette is lighter than the water it's pushing out of the way, or in science we would say it's more dense, or it's less dense than the water that's in there, then, and in this case, the air is less dense or lighter than the water, then it will float. But what I want you to do now is take it out. And remember how I showed you how to use a pipette by squeezing the bulb, putting it into the water and letting go. It'll suck some water in there. I want you to try and fill it as full as you can with water. You probably won't be able to get it completely full. You can see mine's about half full of water. One thing you can do is you can use the end that you cut off your pipette. If you put that into the water and then plug the end with your finger and lift it up, it'll trap the water in there. And then you can use that to even put more water into your pipette if you want to. So you can fill it up, but you don't have to have it completely full. So I'm going to put it in there. I'm going to use my finger to put my finger over the end and then fill it up with water. And then we're going to do the same thing. So we're going to get it full of water. So that's about a little over halfway full of water. And notice, if I'm careful, I can turn it upside down really fast. And as long as I don't squeeze it, the water is still in there, still a little more than half full of water. And that is because the hole, even though there's a hole down there at the bottom, the hole is so small that the water molecules can actually hold on to themselves. We call that cohesive force. Those water molecules are actually strong enough. They're kind of like glue. They can hold on to other water molecules. And as long as the hole isn't too big, they can actually hold together and keep it from spilling out. Sometimes we call that surface tension. That's another term you might hear. about this. And we have some other experiments on that webpage that you can do more experiments with surface tension or cohesive forces of water. But now your little pipette submarine should be about half full of water. And I want you to drop it into your glass again. And this time, does it float or sink? Looks like mine is still floating. Might have to add a little more water to my glass so there's room. And you can see that my pipette, even with half full of water, it's still floating. But now it's just barely floating. If you remember before, at first, when there was no water in it at all, it was floating and it was bobbing way out of the water. See how much the bulb is out of the water? When I filled it half full of water, oh, this time I put a little more water in it. Now it's not even floating anymore. Now it did sink. Hopefully you guys can see this. Can you see that my pipette's down on the bottom? There's so much water inside that it sunk now. So we made it by putting water in there instead of air. That made our little submarine heavier. And now it's too heavy to float, or it's too dense to float, and it sinks. So if it's no water, it'll float. If it's full of water, or even almost full of water, it'll sink. Now let's see if we can put just enough water into our pipette that we can make it still float, but just barely. You can go ahead and experiment with different amounts of water. Depending on how much water you leave in there, you can change how high it floats in your glass. So too much water, it becomes too heavy. Too little water, it floats up at the top. And if you get just the right amount in there, it just barely floats with the very top of the bulb just touching the surface. Might take a little experimenting to figure out just the right amount. And that's exactly how a submarine works. When a submarine wants to be on the surface, it's got these tanks inside the submarine. They're called ballast tanks. And when they fill them up with air, the submarine will float. But if they want to dive underwater, they open up some doors and let ocean water, let sea water come in, and they fill it full enough that the submarine can dive down. And then if they want to come back to the surface again, all they have to do is blow all that water out. So they'll usually have like an air compressor so they can blow more air in, push the water out until they push out enough of the water that the submarine will float back to the surface. And that's exactly how a submarine controls its depth. That's how it dives and surfaces, by changing that. So our submarine works the same way. The only problem is we have to keep squeezing it and reaching into our cup. That's not a very good way to do it. Now we're going to turn it into a remote control submarine. Does everybody want to see how to turn this into a remote control submarine now? So that we don't have to grab it every time we want to change whether it's diving or surfacing. Now we need our bottle. Okay, so now go ahead and squeeze all the water out of your submarine so it's just full of air again. We don't need the glass right now. And carefully take the lid off your bottle. Remember, it should be filled with water all the way to the very top. And then I'm going to drop it in there, and it's probably going to spill some water, but that's okay. That's why we have a towel. So I put it in there, and notice there, since it's full of air, it's bobbing up and floating completely out of my bottle. That's okay. Now I'm going to take my lid, and I'm going to put it on there, kind of push my submarine down, spill a little more water, and then screw it on tight. And so now my submarine is in the bottle, floating up at the top. And if you look, you might notice that as you put it in there, a little bit of water has come into that hole. Does everybody see a little bit of water inside the stem of their pipette? Probably not very much at all, but I bet there's a little bit of water in there. But it's still not heavy enough to sink. It's still floating. But we know what we have to do if we want our submarine to sink. we have to get more water inside it. But that's kind of a problem because we put it inside the bottle and I screwed the bottle shut. I can't reach in there anymore. So I'm going to try something different. I'm going to squeeze my bottle really hard. And when I do that, my submarine sinks. Is anybody else's? You might have to squeeze really hard and your submarine will sink. And when you stop squeezing, your submarine surfaces again. Give me a thumbs up if your submarine is doing that. If it's not, that's okay. I'll show you how to fix it in a minute. But if it's working, go ahead and give me a yay or a thumbs up. Now we have a remote control submarine. When we squeeze the bottle, it sinks. And when we stop squeezing the bottle, it floats. Now remember, if you're having trouble getting it to work, remember there's a couple things to make sure of. Make sure your bottle is filled all the way to the very top with water. Don't leave any air in the bottle at all. That's going to make it harder. And then if it's still, you might have to, like I say, you might have to squeeze really hard to get it to sink. And when you squeeze the bottle, I want you to look closely at your submarine. Do you notice that when you squeeze the bottle, it pushes more water inside the submarine? Just what we wanted to do. And when you stop squeezing, that water comes back out and it floats up. So we're making our submarine go up and down because we're changing how much water is inside, just like a real submarine. Now, the reason it does that is because since our bottle is completely full of water, if we try to squeeze the bottle, the water can't get any closer together than it already is. All those water molecules in there are already bumping into each other. They're as close together as they can get. That's why it's so hard to squeeze this bottle. We're not really making it any smaller. If you ever try to squeeze a bottle that only has air in it, you can squeeze and crush that bottle. But with water in it, it's really hard because the water has nowhere to go. In this case, it does, though. When we squeeze the bottle, it pushes more water into our submarine. Now, is anybody having trouble getting their submarine? You just can't squeeze it hard enough to get your submarine to sink? Go ahead and raise your hand if you're having some trouble, and I'll show you what you can do. Maybe if you think about it, you might already have an idea of what you could do to make your submarine easier to move up and down. Anybody got a thought? How could we make it go up and down easier so we don't have to squeeze so hard? Okay, we got Everett. Everett, what do you think? What could we do that might make it a little easier to operate?
Maybe if you empty just a little bit of the water out.
Oh, you're on the right track, but you're backwards. Think about it and then answer again.
In.
Don't empty a little bit of the water out.
Add more water in.
Add a little bit more water to start with, or you could say empty a little bit of the air out. So remember, we found that if we change how much air there is in there to start with, or how much water there is in there to start with, it changes how easy it is to float, right? So what we're going to do, instead of putting our submarine in with no water, just go ahead and put a little bit of water. I wouldn't fill it halfway, but maybe up to where the washer is or something. Just start with some water in there. And remember, if you don't squeeze too hard, that water will stay in there, even though there's a hole in the bottom. And now put it in your bottle. And now notice it's not bobbing all the way out anymore. It's floating, but it's floating very close to the surface. Now I'm going to squeeze, or now I'm going to put the lid on, screw it tight. And now I don't have to squeeze very hard at all to make it go up and down. Now, if you put too much water in there to start with, what do you think is going to happen? It's just going to sink and then it's not going to come up, right? If that happens, you're kind of out of luck. You have to go over to your sink, dump all the water out, get your pipette out of there, get your submarine out of there, empty some of that water out of the submarine, so don't put so much in there, and fill the bottle with water again and do it again. That's why it's handy if you want to test to make sure you haven't put too much in there. A good way to test that is with your glass. If I can get my finger in there to get my submarine out. There we go. Get him out of there. Squeeze the bottle a little bit, you can get him out. So if I want to test how much water should I start with, you might want to test that in your cup first. make sure your submarine still floats, and then you can take it out of there, put it into your bottle. And again, make sure your bottle is filled all the way to the top. Now, why do I keep telling you that you want to fill your bottle all the way to the very top? Remember, when we ski, if the bottle's full of water and I squeeze it, the water has nowhere to go except to push into the submarine. But if I leave some air in my bottle, so now I'm going to pour some of my water into my glass so that now, can you guys see my bottle's not full? Now that my bottle is not full, if I put the lid on, now when I go to squeeze the bottle, the water molecules may all be close together, but they can just push up and push the air out of the way instead. And so now it's hard. Mine still sinks pretty easily, but if I get all the water out of my bottle, let's see here, get it up there so I can grab it. There, we got him. Let the air out. So now this is a way that you can kind of trick somebody if you want to show them how easy it is to do this, and then they want to try it. And if you leave a little bit of air in the bottle, they'll just squeeze and squeeze and squeeze, and they're just not strong enough to make it sink, because they're just, and if you look closer, you'll see that as you squeeze the bottle, you're just pushing the water closer to the lid. It's not going into the submarine much now. So that's a little trick if you want to be mean and play a trick on somebody. But if you want it to be easy, make sure you fill your bottle all the way to the very top. All right. So is everybody able to get their submarine to work now? Raise your hand if you just can't get your submarine to work for some reason. We'll see if we can figure out what's going on. So let me kind of look around. If your camera's not on, you can use the reaction emojis down at the bottom to raise your hand that way. And we'll see if anybody's having trouble, we can help them here. I don't see anybody raising their hand yet. So it looks like everybody's got their submarine working. All right, good. Let me share my screen real quick and I'll show you what that Cartesian Diver page looks like. And I'll show you some of the other links that you can do some more experiments. So here's the screaming balloons. I'm going to go back to Try Science. Go down to Cartesian Divers. So again, here's the list of what you need. And it explains a couple other ways that I'll talk about in a moment here, other ways you can make a submarine. So here's the one we did, the pipette submarine diver. You can also do what's called a balloon fish diver if you have a little tiny balloon, like the ones you use to make water balloons. And then another way you can do it, I'll demonstrate in a moment here, you can do it with that ketchup packet. So if you haven't got your ketchup packet yet, and you have one in your house, run and grab it real quick. Here's the explanation of the science. That's funny, wasn't it? Huh, got a little defect on my page for some reason. It's not opening up the whole window there. I'll have to work on that. Here's a little more explanation, some other ways you can do that. You can do a real cool experiment with raisins and a bottle of 7-Up that's similar. It's another buoyancy experiment. And then here are all those links. So if you want to do this again and you don't have another pipette, there are other ways that you can make a Cartesian diver using pens and different, like I say, balloons and some other objects. So some of these other links tell you some different ways to do this. This link tells you about the Archimedes Principle. This explains how submarines work. This explains how to do a lava lamp, which is kind of similar to this. This is how you can make a scientific instrument out of this instead of just a toy. And the other one I wanted to show you, so I'm going to stop sharing here. The other way we can do this, I'm going to go ahead and take my submarine out of the bottle. And I'm going to put my little Arby's packet in there. So if you guys have a ketchup packet or you want to try something else, another kind of little condiment package, go ahead and push that in there, spill some more water, make sure it's not stuck in the neck of the bottle. And now I've got my little, in my case, it's a little Arby's packet in there and it's floating up at the top. And now I'm going to squeeze my bottle and I can make the ketchup, I can make the Arby's packet sink. And when I stop sinking or stop squeezing, it comes back up again. So I can actually make a submarine out of a ketchup packet. So you can try that. Anybody have a guess? Why do you think the ketchup packet works as a submarine? Let's see if anybody can tell me why that ketchup packet will work. Well, let's see if I can find somebody I haven't called on yet. How about, I see it says David here, but that doesn't look like a David. It says David and, oh, Cora. Is that Cora? Cora, unmute. And why do you think the ketchup packet does that?
I know.
So, Dave can do it.
All right. My theory is that
What do you think's inside that packet? Think about what's
packet gets
inside that
crushed.
packet.
well,
What's
my
in there?
theory is it gets crushed and it's just so it's smaller and it's displacing less water, but it's still the same density, so it's
You're on the right track. When you squeeze the bottle, the ketchup packet displaces less water. That's exactly the right term. You've obviously done some reading. That's exactly the right term.
actually
It
haven't. I
displaces
just
less
came up
water.
with that.
But the question is, why is it displacing less water when you squeeze on it? What's inside the packet?
Air.
There's some air in there. Exactly. I thought you were going to say ketchup. There's ketchup in there, but there's also a little bit of air. And when you squeeze the bottle, it squeezes the ketchup packet. And the ketchup is mostly water, so it can't get any closer together, just like the water in the bottle. But there's air in there. And so when you squeeze the packet, it just makes that air bubble a little smaller. And when it makes the air bubble smaller, then you said it exactly right. The ketchup packet displaces less water. That makes it more dense, and that makes it sink. When you stop squeezing, then the air bubble expands a little. It makes your ketchup packet a little bit bigger, so it displaces less water, and it floats back up again. So the ketchup packet turns into a submarine. Now this, what I shouldn't call this one a submarine, because this is really more like a fish. Did you guys ever wonder how a fish can, if you have fish in your aquarium, when you put food up at the top, that fish has to be able to surface, just like a submarine, to eat the food. But then later on, it might want to swim down to the bottom to be with its buddies or something. So it has to be able to go up and down. And you probably thought, well, it just swims. But if you ever do any swimming, it's really hard to swim up and down. It's a lot harder than just swimming sideways. And so what a fish does is kind of like your submarine did. It changes its displacement, it changes its density, and it does that because just like your ketchup packet had an air bubble in there, the fish has what's called an air bladder. It's kind of like our lungs. Our lungs are full of air. The fish's air bladder is full of air. And when the fish squeezes that with its muscles, it squeezes its air bladder with its muscles, it makes the air bladder smaller. And when the air bladder is smaller, the fish can sink. And when he wants to come back to the surface, he just relaxes his muscles, his air bladder gets bigger, and he floats back up again. And if he squeezes just the right amount,
Mute.
he can stay at any depth he wants. See how I can make this ketchup packet stay right in the middle if I want? I just have to squeeze just right, and without any effort, I can stay right there. And as soon as I relax, back to the surface. If I squeeze harder, down to the bottom. And that's how a fish controls its depth. Now, I forgot to show you, but you could do the same thing with your submarine. You squeezed and made your submarine sink, and then you stopped squeezing and made it come up. I'll leave it for you to try to figure out how hard you have to squeeze to make your submarine stay right in the middle and not go up or down. You just have to get just the right amount of water into that submarine. All right, so that's our experiments for today, and we're just about out of time here. I think we have just enough time to answer any questions. So if anybody's got a question, go ahead and unmute. You can raise your hand, or you can give me an emoji. You can give a thumbs up if you had a lot of fun today. You can type something in chat. Let's see, I should check. Do we have any questions in our chat? Yep, mine sunk. So let's see, this was ever said it's sunk. Hopefully you fixed it. Mine sunk too from David, but hopefully I showed you how to fix it when it sinks.
Yeah, I don't think there were any
That's amazing.
questions.
We got a wow and an
It's
amazing.
like
All right,
lots
got
of
any
yay
questions?
comments.
Do we have any questions from anybody? Or if anybody wants to unmute and just say something to everybody about how much fun it was?
Is Katie raising her hand? Or are you just waving? No? Okay.
I think Amber, is Amber, you raising a hand there, Amber? Do you have a question, Amber?
Yeah, so does the ketchup packet have to be empty
Does it have to be
make
what?
a little summer thing? Empty?
What are you saying about C?
Does the ketchup package have to be empty? The packet.
Oh, does it have to be empty? Oh, well, if it's, what do you think will happen if the ketchup packet's empty? Try it. That's an experiment for you to try. And I'll warn you, not all ketchup packets work. Because remember, we have to have just the right amount of air inside that ketchup packet to get this to work. So some ketchup packets might not have enough air. They might just sink and never float. Some might have too much air. And just like we were showing, it might be almost impossible to squeeze hard enough to get it to sink. So not all ketchup packets will work really well. So you might have to experiment with a few. But if it's empty and it has no air inside it at all, what do you think would happen?
It would sink.
If there's no air in it, I think it might sink. It all depends on how heavy the package is. Okay, so I think you have to do that experiment and find out. Now you have to make sure if it's empty, you got to make sure you might need to tape it shut or something to make sure no water or air can get into it if it's empty. But I think that would be a very good experiment to try. And it all depends on how heavy the package is. So I think that's a good experiment. That was a good observation, and you should try that experiment. Does anybody else have a question? Maybe another experiment they're thinking about they'd like to try? Like I say, there's more links. If you go to those web pages I showed you, there are several links that show you some other cool experiments. One of my favorites, I'll just share my screen again real quickly and show you the link. One of my favorites, we call it Dancing Raisins, and I haven't actually created our own page yet, but I do give you a link to another one. This one right, Raisins Dance. This one right here called Dancing Raisins. This, I think, is one of the coolest experiments ever. And all you need is some 7-Up or some other fizzy soda pop and some raisins. And so I'll let you guys explore that link later. It is a really cool, it's kind of like the submarine experiment, but well, I won't spoil the surprise. It's really cool. Okay, so I think we're out of time. We've got another, I know the library has another program starting at 2, so we need to check out here real fast. So the other thing I want to mention really fast, on those web pages I showed you, all the instructions, all the links, everything are there. There's also a comment box down at the bottom. So if you guys have any more questions, if you think of a question later, or you just want to tell us how much fun it is, or you want to send us a picture, anything, there's a comment blog right on those pages. And so you can use that to ask us a question or tell us something. So even anytime, and then we'll answer you right away. Okay? All right, well, thanks everybody for coming. I hope you had fun today. I hope you have a fun weekend. The other thing to check our website for is we have a calendar on our website because we go to the Space Foundation, Discovery Center a lot. We're in a lot of other places where you can come and do some more experiments with us. So check out the calendar on our home page and you can find out when you can come and do something else. And I'll give you a hint. We make ice cream a lot. So if you like to make instant ice cream, you should check our calendar and come and see us when we're doing ice cream somewhere. Okay? All right. Well, thank you, everybody.
Thank you.
Thank you for
Bye.
coming.
Bye.
Thanks.
Have a great
Thanks,
weekend.
Mark.
Bye.
Bye. Have a great weekend,
First, bye
everybody.
too.
Bye.